that. All right. Yesterday, after you asked, I made sure that the slides got posted, but this morning I'm going to repost them with a few additions that I made last, include a homework problem from this section. Now, I would like you to turn in, and I'll explain the problem later because it has to do with the material I'm presenting today. So this is just a statement of the problem, but it's not supposed to make sense right now. It'll make sense in about an hour, okay? I will come back. And this is supposed to be a recap of where we left off. So we explained why are we studying recoupling? What does recoupling mean? What we need it for. And then we had a kind of a trivial introduction to a famous heteronuclear recoupling called Redor, and a more of an in-depth introduction to an everyday recoupling called Hartmann-Hahn cross-polarization. And we use that in an experiment called CPMAS, so like the everyday 1D. And we used Magnus expansion and Baker's Campbell-Hausdorff to derive an expression at the bottom of the page, which is the growth of carbon magnetization starting from proton magnetization during the CP. That's my sum of everything we did in an hour and a half yesterday. And I'm just saying all this to trigger any questions before we move on. If not, I'm going to tell you where we're going next, which is much cooler. So two things, if we're going to use this to move from nitrogen to carbon, and like a HNCO was a typical 3D, or it could be run as a 2D for assignments, okay? If that's what we want to do, we want to move magnetization from CO to N. There are a couple of things that are going to be different. We're going to have to add the magic angle spinning, which we didn't mention here. And we also want to talk about whether you're on or off resonance, because it's cool to be able to control whether you move from nitrogen to Ca or CO or both. That's a really nice thing to be able to do. And we have a better way to do that than like comes up for solution NMR, which is just based on the strength of the J coupling mainly. But over here, we can do it based on the chemical shift and this coupling. So here's what we're going to do. We're going to think about the offset, the chemical shift offset. And that offset and the RF irradiation, like the very first lesson or the second one, Art talked about this, like on resonance, off resonance, what happens to your pulse time and how to think about it. So you have a B effective, which is like your offset of B along Z and your B1 along X. That's a picture in the rotating frame, where B1 would be a static X vector in the rotating frame. And then delta B would be how much are you off resonance. And so their vector sum is what's important in this frame. So we're going to use that as a tool. And in general, you can't be exactly on resonance, because even if we're talking about different carbonyls, they each will have their own isotropic shift. We're trying to build up a 2D here that's resolved. So we need to put this into our picture. I took it out to simplify for yesterday. And now when we're trying to talk about reality, we have to put this back in and the MAS. So what we're going to talk about is assuming that there is an offset. And so we don't have B1, we have B effective. And what that means is that the right frame transformation is not around B1, it's around B effective. And the way we do that is that we build it up as being two steps. two frame transformations to take care of both the offset and the V1. First thing is a once and done move to the tilted frame. So we start out in Z is Z, nothing complicated. And we move to a frame where our Z axis is the V effective. It's just one operation. It's not time dependent. It's just something that happens for the whole pulse sequence in one go. So that is a rotation through an angle, which is the arctangent of omega 1 over delta. Then we have a time-dependent transformation where we rotate around V1, which is our new Z-axis. And what do we rotate at? The effective frequency, which is the sum of the squares of omega 1 and delta omega. All right, so this is very similar to what we did yesterday, where we're doing a frame transformation and A was V1. Now A is the vector sum, and we need to tilt down into it first, okay? So this is the tilted frame, and we have to do it in principle on both channels. So we talk about double toggling, double tilted frames. Jargon. So the double toggling interaction frame follows the net action of both RF spin locks and corrections for frequency offset. Main static field has already been included. We began it. So this is A. Now, A includes an offset and a B. So what happens when we take the same litany of Hamiltonian terms and we do a doubly toggling interaction? Right. So by construction, it is removing the chemical shift offset and the spin lock. That's what it does. That's what it's made of, okay? And it's still the same that the homonuclear dipolar, we can set things up so that we commute with that. We don't know how to make it fully go away within this family of sequences. It's not gone. But we can say, well, it's not going to do much because I'm going to choose to set up my pulse sequence so that my initial magnetization commutes with this. So I'm going to ignore it. This is the error of everything I'm talking about because it isn't really zero and it does really matter. Okay, so that just remember that this whole simplified analysis does have a flaw. But the heteronuclear formally is still there. It's simple. It's a nice simple Hamiltonian and we can control it. We're going to pretend like it's the only Hamiltonian going on. Oh, by the way, of course, you could also introduce isotopes so that the homonuclear dipole really wasn't there. And those pulse sequences always work there. So magic angle spinning and heteronuclear couplings. I don't see who all is on. I know there are more people than I'm seeing, but thank you. I just wonder if we need to just tell Anish where we are. Thank you. All right, so magic angle spinning and heteronuclear couplings. So the effect of magic angle spinning is to make the dipolar frequencies time dependent. This is the moment that we put this back in. Besides the fact that homonuclear couplings are a real thing and that we cheated, this second thing that we're not doing right here that I want you to be aware of, and it will be highlighted in some other things that come up or in some other papers that you might read, we didn't put chemical shift and centrifuge in this problem. We only put isotropic shifts. So we're still oversimplifying in at least two ways, okay? But we're going to put the offset and the MAS in. Now, the dipolar MAS, we solved this problem several weeks ago. It is whatever the static maximum value is, which depends on R and the gammas, and it has two different sinusoidally varying terms. Now, sine 2 beta, I'll remind you, that's the crystallite selection, as is gamma. But the important thing is that it's sinusoidally varying with time. The important thing is this is time dependent. Okay, everybody remember what all these symbols mean? It's okay that I'm not redefining them? Yeah, okay. So we have to add this time dependence, even in the rotating frame, there was a time dependence there. And what happens to it? So we're ignoring everybody else. What happens to it? I didn't want to go to a micro mini font. So we have the next slide. Okay. Oh, we're in the wrong spot. You found us.
Yes, sir.
All right. So we've talked about being in the tilted frame, and now we're talking about putting the MAS back into the problem. So here's time dependence due to the rotor in here. And here's the tilt of the initial frame transformation to the tilted frame. Okay. And now we're going to go to MAS. Okay. And you have the tilted frame. So that took what was just an IZ operator and turned it into an IZ plus a little bit of IX in the tilted frame. So you rotated around Y and got into the tilted frame. And then look what happens to that IZ plus IX. Keep your eye on the IX. This is rotating around Z in the tilted frame according to an argument omega-1 for that spin times time. Okay? So this bit out in the front is the spin degrees of freedom. This bit at the end is the spatial degrees of freedom. Spatial degrees of freedom are modulated by MAS. Spin degrees of freedom, so once and done tilt frame transformation, and then a continuous time-dependent sinusoidal variation because you've got the RF on. In this frame, this is what you have, the two time dependence. So we're in a scenario where we have just this one term of our Hamiltonian being active. And then it was actually an elegant little term before we started messing with it. But now it has two different time dependencies, spinning and RF. And they relate to each other multiplicatively, right?
Do we have nobody online?
Yeah, we have 5.
Oh, okay.
I don't know why it looks that way. I don't get involved with it. But you guys can hear, and I heard you earlier, right? So everything's still good, Krishna?
Yes, I hear everything and I see everything. Thank you.
Okay. So you have to just jump in if you have a question. I can't tell if you're raising your hand, okay? I forgot to say that.
Can I ask this T, this like superscript of sine omega-1 effective? Is that a superscript, or are you saying?
No. I had a typo where I forgot it.
Okay.
I left the T out, and since this is all about everything being time dependent, I decided that was an intolerable typo.
Okay.
But I can't edit these equations right now unless I pay a lot of money or become as virtuous as art is. So I just put it in there.
I see. Okay.
Sorry, that looks like a superscript. I guess it's better than not having anything. So down here, this was in. The MAS time dependence was in. I'm actually emphasizing that there's also an omega-1 T dependence, but I had no T, which was sad. Thank you for your question. Okay, so the spin transformation is this bit. The spatial transformation over here is this bit. That makes sense? So we have two time dependencies and they get multiplied by each other. Do you guys have any thoughts about that? Having two time dependencies like that, like an expression like that, what does it make you think of? Hope for? What does it make you want to do? Quit the class? Do a specific experiment? What do you want to do?
Cry.
Cry? Yeah? You'll feel better. Go ahead. Do we, this is the term, what do you remember the big picture? We're trying to keep this term or throw it away? What are we doing? The heteronuclear dipole coupling, what are we trying to do with it? We want to keep it. It's okay. I ask very simple questions. You don't have to overthink it. So we're trying to do a CN transfer. We want everything else to go away. We want to keep it. And then what was the problem? The problem was the MAS was making it go away, right? All right, now we've got a pulse and the MAS. What do you want to do to have this stay positive? To add up to something. What would you like to do in this scenario? You know, a trick to make the product of those two time functions not cancel out, a kind of rectifier. It's what I used yesterday. Cosine squared has an average. It's non-zero. It's about it is half. Okay. Sine squared has an average that's non-zero. It's half. So the trick you'd like to do is to do what? To make this look like cos squared, you're going to do what? You're going to set omega 1 exactly equal to omega r. That's what you're going to do. What else could you do? What else might work?
Set omega r.
Set omega 1, I think this is what you just said, equal to 2 omega r, right? Those are two things you could do right away, and you would have an integral that would be non-zero over the rotor cycle. That is a Hartmann-Hahn. Matching it is, but it's not the same thing we talked about yesterday. Yesterday we said that you set omega 1 equal to omega 2, and now you might have omega 1 equal to omega r, but we actually have a three-way match that we have to worry about here. So we haven't quite said the right thing yet, right? You're in the right ballpark, but you haven't quite said the right thing. What we're going to do to make more sense out of this, at the very beginning of yesterday's lecture, I said, I'm starting to write things Cartesian. Is this bugging you? And you guys didn't say anything back to me, sadly. You were quite neutral about the topic. And I said, well, you all can go home and do it in Cartesian. I don't know if anybody thought about that, but in the end analysis, I always like to see it more as spherical harmonic type organization, because it has to do with what these terms can do for you. And in order to reorganize IS type terms in terms of what they actually do as a mixing element, you're going to disentangle secular terms from double quantum, from single quantum, from zero quantum, the same exact concepts that have come up for the solution NMR already. And there's an old piece of jargon, NMR has so much jargon, which is the dipolar alphabet, as Abraham used to talk about it in his book, which is not a new book, is still very relevant to look at, to have in your library. So the A term, that's the secular term. B is zero quantum, which may or may not act like a secular term. That depends on if it's homonuclear or heteronuclear. C and D terms are single quantum type terms. E and F terms are double quantum type terms. So what we want to do is organize these Cartesian operators, X's and Y's, X's and Y's, so that they look more like spherical harmonic, so we can tell if they make things rotate, if they flip things, if they flip both, what are they doing, okay? And I like the zero quantum terms, personally. Most people in NMR really like double quantum terms. I like zero quantum terms. So I started out by fishing out the zero quantum terms. And those always look like promote one, demote the other. That's what it means to be zero quantum. So you end up with the same M sub S overall. And I just went back to my notes and I rewrote them in terms of IX and IY. You guys can check this. It's a really good exercise. See if I made a typo. Okay, but I think this is correct. And so now I have IXSX and IYSX and all those good things. Okay, so I can rewrite my Hamiltonian as being flip-flop terms times time dependencies of things. It's just tedious. It's not even quite algebra, but you just have to sweat the details. And it will not change the fact that, that you have sinusoidal variation in space, according to omega RT, sinusoidal variation in spin space, according to omega 1 I and omega 1 S. And then these things I call projection factors, those are what happened when you went into the tilted frame, okay? And they are, again, not time dependent. They're just like a one and done thing, but these are time dependent, these are time dependent. And now I have to ask again the same question. What do we want to do? Well, this is the term we're trying to preserve. So I've got cosine over here for omega RT. And then it's cosine omega 1I and cosine omega 1S. So they're all three multiplied by each other. So what is it? What is the rule for that sort of triple multiplication of different arguments for that to be non-zero? Well, I feel better when I do that as an exponent. You can look up your trig. You can answer it as a trigonometric function. It's okay. This is the answer here, but let me give you the justification when I reconvert it over to being exponents. Okay, so you know that sines and cosines can always be written as complex. And when you do that, you see that the terms look like this: e to the I omega 1, e to the I omega 1s, e to the I t. And what do I want one of these terms to look like so I get an integral out of it? That's non-zero. I want it to be 1, so I want the argument, the exponent, to be 0. And now I know what the selection. That's really easy to recognize what I'm trying to do. They're not all going to go to being something at the same time. So in this game, even for one interaction and one sub piece of that, it's just a 0 quantum piece from inside a heteronuclear dipole, you'll tend to pull certain pieces to be non-zero, and other ones, you left money on the table. And so you're going to be ending up with the question, was that the best? Have I optimized? And there's a game of optimization which is not converged in the community yet. Not converged. And some strange things do better than the first thing that enters your head. But anyway, you're trying to get one of these to look like e to the 0. That's all. So this is easy to know why the rule is what's up at the top here. For the 0 quantum piece of the heteronuclear dipole condition, matching conditions look like the difference in the Rabi frequencies for the two channels is the rotor frequency. You guys remember what it was for the static case? What was the Hartmann-Hahn condition for the static case? And yeah.
Is it just the Rabi frequencies are equal?
You set them equal. And now that won't work. But if their difference is the rotor frequency, then overall you have something that you're going to keep. Yeah, so that's a 0 quantum matching condition. And I said everyday CPMAS experiment. And that's why when you looked at those pulse sequences I drew, the two spin locks were generally not drawn as the same height in the cartoon. It's just a reminder for us that you set them to be different to match this condition. Okay, so the evolution under this Hamiltonian is going to be exactly the same problem as yesterday. There's actually no difference. So matching condition is met, then you have the buildup according to the same expression we looked at yesterday. And you start on proton X magnetization, you end up. We're going to look at some actual data later. By the way, there are also double quantum operators inside that Hamiltonian. And when you work those through and you pull those geometric factors out, it's a different matching condition. So you can do a double quantum transfer or a 0 quantum transfer. Those two experiments have a different optimal rho naught. So usually we don't get to choose rho naught that much because the premise of this is that we've got nothing on carbon. So we just are going to have something on protons, and that's it. But if you could choose anything as your rho naught, you would pick something different. That comes up when you're measuring a distance instead of just trying to polarize something. So if I'm going to measure a distance, what I really like for a 0 quantum is to start with population difference. And what I really like for a double quantum operator is to start with them both polarized. But the context we're doing here, we don't really have so many choices. We just start with all the proton polarized back to equilibrium and nothing on the part. That's just where we start. It's not optimal. So the expression takes on non-zero values for the sum is equal to a rotor frequency. The sum is equal. It's a practical difference here that we'll get into in a little bit. But that's just how they behave. We don't need this. Yeah, here's the practical thing. So B1 required for the zero quantum condition isn't very good for fast spinning probes. So we're definitely not going to be using what I call the 5/2 condition. So what I mean by a 3/2, 1/2 condition, for example, is I'm going to put omega 1 for the protons, for example, at 3/2 omega r, and omega 1 for my carbon, I want it at 1/2, and then the difference is exactly omega r. For reasons that will come up later, we like these half omega r situations, so I'll talk about that later. But let's say I want the difference to be, one of them has to be higher than omega r, and when omega r is really super high, that's not that easy to do. You may not be allowed to do it for a particular probe. So when you look, by contrast, at the double quantum, it's that the sum of them has to be omega r. So they'll both potentially be below omega r. So it could be like 0.8, 0.2 times omega r, and that's usually feasible for most probes. So old school, we always use these zero quantum because we were trying to get omega 1 to be high to have more perfect behavior with our slow spinning. But now that fast spinning is popular, now you see a lot more work with double quantum or modified double quantum, like slightly off the double quantum for various reasons. Okay, so summary. Transfer theoretically depends on crystallite angles, chemical shift offset, distance, and things like that. You have these two different matching conditions, but in practice, there are lots of things that come up that aren't these things that we have in the equations. In practice, mixing times much longer than what you would think from the coupling are used. Whatever the probe allows until the signal starts to decay away. So crystallite angles really don't matter that much, and longer distances actually can be successful. Practically, it depends on homogeneity and stability of the RF. Very big deal. So what is homogeneity of RF, anybody? What are we talking about?
It's like the B1 opportunity.
Yeah, what is that?
How homogeneous like the magnetic field is throughout the entire set.
Yeah. If you've looked at the insides of a probe, you know it's it's just a wire, just round around. It's just like if you take your pencil and do an odd wire. They do it better than that, and they use better material. And really, it's the same thing. And your finite element analysis, or even just intuitive picture of what the B field around those windings is going to be, it's not going to be very homogeneous. So there are tricks, compensated coils, things like that, to get it more homogeneous, but it's not perfectly homogeneous. So different parts of your sample have different B1 fields. And that's a design criterion for a probe to try to get that a little better. But these matching conditions need to be tolerant somehow to that. What about stability of RF? What are we talking about there? It's not a trick question, just like whatever you think is okay to say.
How consistent it is
Over time. And the weak element, and I'll tell you that I did this when I was frustrated trying to do experiments like this. If you take a heat gun, like those big hair dryers, except it's for the lab, and you walk around your instrument, there is one part of your instrument you're going to get to that all hell breaks loose, and that is the power amplifier for the pulses. I thought it would be the receiver. I thought it would be something delicate. I thought it would be something important on the receiver end. I was wrong. Get to the power amplifier. It's like, oh my God, that's my problem right there. Because I didn't have temperature stability in the lab, that power amplifier. And the Bruker instrument, they have self-compensated. So they have a feedback loop. So when the room temperature changes and the amplitude changes, there's a feedback loop inside the instrument to go back and compensate that. And it works super well. So you're not aware of that and it's not affecting your experiment. but there still can be reasons why your pulse is not 100% stable over time. Could be your sample, could be the temperature of your sample, that the impedance mismatch when it's the sample is changing because the temperature of your sample. Like there are all sorts of reasons why the RF might be unstable over time. These are the things that more than anything else affect a Hartmann-Hahn experiment. RF homogeneity and stability and the spinning frequency, but usually you shouldn't be doing the experiment if that's not stable. These are the reasons people use ramps, because you could be right on the condition when you set it up, and then you could go home and come back the next day and find out you drifted off. In fact, if you, when you're doing some of your first experiments, you're doing CPMAS, you should set up without a ramp adamantane, like some really simple compound, and just see what it does overnight. And you'll see what I'm talking about. Ramp, we looked at them. The pulse sequence is like one of those two spin locks is not flat. It's like a trapezoid, like the omega 1 is a function of time. Could be linear, it could be something fancier. Okay, that raises the question of how close is close enough. When you look at a match condition like this, okay, it's a double quantum match condition. If I rewrite that as being omega 1I plus omega 1s minus n omega r is about 0, how close to 0 do I have to be? What delta would be tolerable in an offset? Do you have a feeling for that physically? Any opinion?
Like depends on how long you're integrating.
The length of time, maybe it could. It would, but it's more fundamental to say that it depends on the strength of the interaction, which in turn informs how long you should be doing this. So the interaction, you could think in kind of a hyperspace. The interaction is one dimension, and this match or mismatch is another dimension. And when the mismatch begins to be big, then you're actually not having a very effective Hamilton. So big compared to what? Big compared to the very interaction you're using here. So the strength of the heteronuclear dipole couple. So what for us would be about a kilohertz. If you're off by 100 hertz, it doesn't matter. It doesn't matter at all. But if you're off by a kilohertz, you're not doing a stable experiment. That's not your chemical shift offset. It's the offset to that match condition that I have. Don't be off by a kilohertz. Don't freak out if you're off by 100 hertz. But that's what makes it hard to use these experiments. We did when Chad was here, he and I did some experiments. We would try to use Hartmann-Hahn to go out to like 5 angstroms and get tertiary contacts. And it works only if you really hyperstabilize the instrument. It's not practically a good choice. So practically, more than anything else, this depends on accidentally hitting other conditions. You probably will not miss the condition you want it to be on. What might happen is that you hit another condition. And so this is a good segue to the second half of this lecture, which is about other conditions. Yes, please.
What theoretical or practical aspects other than power handling will affect the relative efficiency of matching the sum or difference to twice the spinning frequency?
Twice versus single. It's those projection factors, I think, more than anything.
Oh, yeah.
They're different. And I think the first is usually better.
I see. To get better efficiency generally.
Now, if we could see the anisotropy in this, then you'd actually be picking up different crystallites. Sort of a funny trick, right? But we don't see the anisotropy, a topic we can talk about more later.
Yeah, so I guess if you had an isolated spin pair.
Yeah, and you cut it off early, like you don't transfer very long,
Yeah,
you don't let it diffuse.
Right.
So for double quantum matching at very high spinning speeds, do people go to the n=2 condition so they can get somewhat larger V1 fields?
No, I don't think so. I think in practice, the idea is because omega 1 is so high, omega r is so high, this is a problem. So we want to come down to below MLR. Today, exciting is 160 to 200 kilohertz, and then a V1 sort of keep pace because in order to get fast spinning, you've miniaturized your rotor, and therefore you could take the V1 up higher, but eventually you're going to hit that arcing again.
Right, but your 0.8 0.2 condition for double quantum would be one of the fields.
It's really weak.
Right.
Yeah, and in practice, this hasn't really been the biggest problem, which is sort of weird. I mean, I'm sure it's a problem for some things.
One of the things it works out for is that for proton detected experiments, for carbon proton detected experiments at the spinning frequencies, you often want to limit the carbon indirect dimension. So you end up CPing
Deliberately selective. It is deliberately selective, just like the NC.
as
And you
opposed
also
to
can
the-
ramp it and sweep it, and people do this.
yeah, as opposed to a broadband high power CP at
Yeah.
slow spin.
Yeah, so people are, I don't know, celebrating the virtues of it. It's gonna be a limitation for something. Sure, you're right. Okay, so I said it shouldn't be a problem to be off the condition if you're on a one bond and you set your instrument up carefully, you calibrate the pulses, everything. But it could be a problem that you don't think it through and you hit another condition. So you hit the condition you're supposed to, but you're also at another condition. What am I talking? Let me give you an answer by example. Something called the horror condition, which recognizing and thinking about this condition, I attribute to Niels Nielsen when he was working with Malcolm Levitt. Analogous situation for homonuclear dipole couplings, non-selective pulses. Suppose omega-1 happens to be omega r over 2. So like that 1/2, 3/2 condition, you would have one of them at omega-1 is omega r over 2. Then the homonuclear coupling can evolve. So why? Because let's write that homonuclear Hamiltonian again, the one that we've been ignoring, even though we know it's real and it's happening. So it's in the interaction frame. Looks like I didn't put the tilt on this, but whatever. So let's say we're on resonance. There's no tilt, but we are in a frame where we've bucked out R1. So we have this cosquared omega-1 T in front of our spin operator. And over here, we have 2 omega R T for the rotor, okay? Well, this is very analogous to the heteronuclear, except in that case, we had cos omega-1 and cos omega-1s. Now we have 2 copies of cos omega-1 T. This kind of a situation will be non-zero overall if omega r is twice what omega-1 is. It's just analogous to the zero quantum conditions for the heteronuclear. There are also conditions that I don't know if we'll have time in this class to talk about, but they act for the CSA. I'd like to do this, but I don't know if we'll have time, but I just want you to be aware of them for today. There's something that was discovered by David Grant that only needs a CSA and spinning and nothing else. It doesn't have a dipole coupling invoked. So if you spin and you hold a spin lock, so we just have that spin locking field and we have the rotor and we just have a CSA, then you already have some interactions. So we don't need 2 spins for this. And omega-1 and omega r, if they happen to be matched, okay, then we will retain the CSA term. So in our original problem, this didn't come up because we left out the CSA. Now I'm just showing you something about the CSA. It has time dependence. We derived this weeks ago. If I put that time dependence together with this frame transformation, I discovered that omega r times omega-1 brings back powder patterns. You would see this on your spectrum, that suddenly your signal becomes weak and anisotropic and looks like a little mini powder pattern because you're spinning at a bad frequency compared to your spin lock. Sometimes called rotary resonance conditions, sometimes called R cubed, chemical shift conditions. This particular one has had a lot of different names and it's vexing. People forget about it and then they get messed up spectra. So I learned early on that if you want to do these Hartmann-Hahn conditions, you probably should have a spreadsheet until you've memorized it all. So you've got omega-1 I, you've got omega-1 S, and assume that omega r has been selected on some principle and is fixed. And now you have a 2-dimensional space, and it's a minefield. There are things to stay away from, like magic lines, like those laser games kids do, okay? And there are islands that are good, like 3/2, 5/2 condition is very, very good. Or 0.8, 0.2 is pretty good. That's a double quantum condition. So 3/2, 1/2 sounds good because you're not pushing the probe. It's not a good condition. It has horror right there. Right, so 3/2, 5/2, or 0.2, 0.8. There are certain places that are good. And you begin usually by thinking, what chemical shifts do I have and what spinning frequency can I do that I will like? And here's one more condition that I'll mention that was built into choosing the spinning frequency. There's a condition called rotational resonance. I did a lot of work with rotational resonance a long time ago. Nobody uses it anymore, really, but it was found in the Griffin group by a group of people, including Dan Raleigh and Malcolm Levitt in the very early 90s. And then I got a chance to do some of the bio applications with it. You have two spins you're interested in. They have isotropic shifts, of course. You want to see what the distance is between them. So we had some things in proteins, we want to measure the distance. And they're not coupled because you're spinning. You don't know about any pulse sequences, but what you do is you set the rotor frequency so that it's exactly the difference between those two isotropic shifts. Delta omega iso equals omega r. Then those two spins will talk to each other, but no other pair of spins will. So it's a very clever, cute thing, and it was actually independently discovered in Ernst's group at the same time as we were starting to work on applications and discovering it in Bob Griffin's group. So that matching condition can be used to do lots of things. We used it to measure torsion angles, distances, all different kinds of things. But I think it's been sort of supplanted by cleverer methods so that nobody really needs to use it anymore. But you do need to be aware of it. And when you pick your spinning frequency, you don't want to accidentally be at that condition. It really messes things up in a serious way. So in this minefield picture, I said, let's first assume that we're spinning at 85 ppm for carbon, or above 160. So that's important. You've got your uniformly enriched sample, whether it's nucleic acid, sugars, or proteins. You need to figure out where your carbons are when they're directly bonded. Do not be at rotational resonance for them. So for proteins, that means you go to 85 ppm. For DNA, we'd have to figure it out. Like where do we need to be for DNA? There's going to be some rules for that too. And in the literature, you see people are not always that careful about this. And I think that introduces systematic error for sure. And then, of course, there's a practical concern that you can only pick conditions that your hardware is stable to do. So this minefield is a theoretical one, but then only some parts of it are possible.
Dan was a graduate student when he found this, and he says he found it by accident. He just set the machine up wrong, and suddenly there were peaks that he didn't expect.
Well, it was the disappearance of peaks. I was there when this happened. So he had this dumb compound that he was going to do a much less interesting pulse sequence on, zinc acetate. Anyway, and he was just, he was ready to start writing. He had plenty of things in his thesis already, and when he would get to these conditions, the spectrum would just disappear. And I was like, yeah, well, you can set it up right. Obviously, your peaks are okay. But look, when I go faster or slower, they come back. And then Malcolm explained it. Okay, so summary. Transfer theoretically depends on crystalline angle, CS offset. In practice, you use very much longer times. Depends, therefore, on stability, homogeneity. You should use ramps. How close is close enough? That whole coupling. And this last comment, be aware of other conditions. Finally, whether the sequence works or not depends on so many things that are about your sample. And really it's down to the relaxation, the R2, the exchange terms, the R1 row. And that depends on the motion. So temperature, hydration, formulation, these are really, really important. And this is a nice example that Chris Juraniak selected for a different course that we do in alternate winters for biosolids NMR. And he's just showing, and many people have shown this for other examples also, that if you have well-formed proteins, that could be crystals, it could be fibrils, you can get quite narrow peaks under CPMAS with decoupling. But if you have dehydrated or lyophilized, you may get more signal, but a much uglier spectrum. Okay, so a lot depends on the formulation of the sample. But if the sample is well formulated, you can also have a lot of success with carbon transferred to N15. This is the double CP experiment here performed on ubiquitin, and I'm not going to get into the details. I'll just say that that was measured here by Chen-Ming He and Keith Fritching and Eric Keeler on ubiquitin CN correlation. This is a very standard experiment in the repertoire. It's a good working plane. There is a picture here that you see often in many articles. I picked one from a material science paper from Helmut Eckert, but you see this a lot. That there's a picture that is important that for Hartmann-Hahn to really work, not just on paper, that both I and S are in a bath. They have friends. They have other versions of that spin, and both of them are connected to what we call the lattice. Now, the use of this jargon, lattice means that you're in a molecule, and that molecule has things like phonons and movement. Bath means that you're on a particular nucleus and that it has a network of couplings into other types of that nucleus. So all of this has to be there for the Hartmann-Hahn to actually work in practice. So there's a lot of spin diffusion into the rest of the nuclei around that stabilize the experiment compared to a single spin pair, which in practice wouldn't have worked as well. And that when we measure cross-polarization, we know empirically that there's a growth period. We don't see the oscillations very well that our equation predicted. They're in there. If you digitized on the microsecond time scale, you'd see a little bit, but mostly you just don't see them. And then you hit a maximum, and then it decays, and that decay is governed by losses in the proton bath. So you're staying connected to the protons, and they have a relaxation mechanism always. And then it decays. So empirically, we find a maximum, which is typically between 1 and 4 milliseconds. So these equations that we looked at govern the early time behavior. And sometimes that's kind of softened by relaxation phenomena so that it doesn't look so oscillatory. And sometimes we just don't digitize them, so we don't know if it's there or not. You can use the buildup time, early buildup times, if you have an isolated enough spin system. Those oscillations can be Fourier transformed to give you a powder pattern, and that powder pattern can be a somewhat quasi-quantitative indicator of motion and order parameters, such as this study of ubiquitin carried out by Justin Loriot, where different C alphas have different widths and shapes of that dipolar pattern. So you're transferring from hydrogen to carbon, so we're talking about a one bond dipole coupling. And if it's rigid, it would look one way. If it's large angle, fast limited, look another way. If it's small angle, fast limited, look another way. So you can see those early oscillations in Fourier transform, but normally we're just doing something like this. We're just trying to get some magnetization, and we're looking for the optimum around 2. Okay. Now, in terms of the motion, one other thing I want to mention, I began by saying you could do inept. And then I said, that's not that great because of T2. But in a protein, you may have mobile and immobile regions. You may have like tails, and in C termini, mobile loops, versus the globular, really well-folded things. And in practice, near room temperature, you can try that inept experiment or related. It could be through J. It could be a very short dipole, but you could look for liquid-like signals, including by the J coupling. And then you could use dipolar sequences where, because you're doing long contact times, you're insisting that that's a stable dipole that stays put where it is. So you're looking for something that has a very rigid order parameter. And you get 2 different subspectra near room temperature. These are different parts of the protein, and they both could be assigned and analyzed. And it's a general phenomenon. Most proteins will show something in each of those 2 spectra. And there's a nice review article, but maybe more of this has to be done, where you look at what is the range of motions and what is the range of order parameters where inept is going to be the spectrum, and what is the range of order parameters and time constants where you expect to get good CP. And then this white thing here is what I like to call no man's land, or I like to call it an inverse Goldilocks. So there's a middle ground that is just horrible. And then if you're more rigid, beautiful CP, that's where you can do the Hartmann. And if you have a terminus and it's got the same kind of dynamics that you have in solution, it's nicely hydrated, it's out there doing its nano to picosecond correlation time thing, then you can just do solution NMR. And we missed some things. We missed some things in this no man's land, and I think it's one of the grand challenges to have the right set of tools to bring those residues back because they're usually interesting. So that's just a heads up to realize that when you do CP, if you find that you're missing something you were interested in, there might be a good explanation. You might be in good company. Also, if you just stay with the CP and you vary the temperature, there are many studies, many proteins done in many labs that show profound temperature dependence and intermediate temperature regimes where you get more of this no man's land business going on. This happens to be a really well-folded protein GB1 that Angela Gronenborg taught us would be our best ever model system, and Chad Reed studied the heck out of it. And so this is like a temperature dependence of some CP data on that system. But you see the same phenomenon in SH3, ubiquitin, that you can see signals going in and out of that intermediate challenging regime. Now, I gave you one example of a homonuclear recoupling a minute ago. This horror, but that's not really what people usually use. It's good to be aware of it, and there are pull sequences that make use of it. But when people do carbon-carbon correlation spectra, let's talk about what they're using as that element. Malcolm Levick likes to say there's a whole flora of pull sequences. There really are a lot of them, and it's kind of confusing. I think it gives everybody a headache. Krishna already has a headache too. Like, it really gives all of us a headache to think of all these different homonuclear recoupling sequences. And we talk about this one's good for that and that one's good for this, but they are quirky. Some early important observations of how to move carbon magnetization to another carbon. Beautiful sequence, really conceptually nicely done, is Drama from Ratico. I already told you about the early days of rotational resonance, which we also called R squared. So that's pick a funny spinning frequency. A little bit by analogy with that, soon folks thought of a pulse sequence I'm going to ask you to do some homework on, which is the radio frequency driven recoupling. That is a rotor synced pi pulses, one per rotor period. And we're going to think about how come that helps you move carbon around in a molecule, a magnetization in a functional group. Since in proteins, amino acids are strung together with a nitrogen, we think about to the first order that we're moving carbon magnetization all around in the amino acid, but not to the neighbors. If we pick a good mixing time with any of these sequences, you're going to get a subspectrum of that amino acid, and it's busted up by weak couplings to nitrogen. And so you can hop to the next amino acid, but in first order, you're just looking at a medium to short mixing time. You're thinking subspectra. Each amino acid, I'll assign each amino acid in the big spectrum. RFDR is a popular way to do that, and you're going to analyze that for your homework. I always really like the dream mixing sequence. That was from Bayet-Meyer. It was a little bit later on, and it uses smooth changes in amplitude and a weak spin lock, so-called adiabatic modulation. We can talk more about that later, but it deserves its whole lecture. That is semi-selective in the way that Anish was talking about some of the heteronuclear sequences. You could use DREAM to just go COC beta or something like that. And just conceptually, it's just a little. DAR and PDSD, that's like, maybe we didn't have to work so hard. Let's just store it along Z and see what happens. See if we can get lucky with some correlation functions and some relaxation theory. And if it doesn't go very well by itself, what we're going to do is sit on the protons and put them on a horror condition. So they're like really hypercoupled with the protons. They were already a horrible bath. Let's make them worse. What does that do? During the mixing element, it broadens. Every single carbon was sort of broadened. Now it's like really broad because it's coupled into the bath that's just a big, big mess. And so it makes the carbons talk more than they were. And so those are both spin diffusion methods, one with a little assist on the proton side. We don't believe that there's very good physics to go with that. So we interpret those non-quantitatively. But it's the easiest thing to learn to set up, and it works. It even works a little bit at high spinning frequencies. So that's a kind of go-to sequence for everybody. But you don't measure distances with it. It's like relayed transfer in the extreme. Like we're happy to relay it. Like we're just trying to get it all. It's like a Toxie-ish thing. Now, again, your homework. And I'll say it again at the end. So now that we've said what this is for, let's look at it for a minute. There's a cartoon of a DAR sequence in context. We begin by exciting with a proton 90 and a CP Hartmann-Hahn. But there's no ramp on this, and it doesn't show that it's got the rotor frequency difference. So I don't like this cartoon because it doesn't teach everything we just learned, but whatever. Okay, that's getting to the carbon. Now, this first element is just to measure the carbon shift while you decouple the protons. Then you store along Z with a pi/2. And then when you're done mixing, you hit it with a readout pulse, pi/2, and then you would measure your FID back here. So we're not analyzing any of that. We're just talking about what happens during the mixing. The homework is just about from that pi pulse to that pi pulse. What's going on? You can assume that you start with like X magnetization. Okay. Oh, I'm sorry. X magnetization before the pi/2. So Z magnetization at the beginning. Okay. And then you're still in some kind of Z magnetization at the end, and then you hit it with a pi/2 to read it out. Okay. So that's your analysis, is from the pi/2 to the other pi/2. Now, what's the pulse sequence? Let's just be sure we're reading this correctly. It has one and only one pi pulse for every rotor period. And the pi pulse could be assumed to be sort of idealized. So it's short. So it's like a strong short pulse in the middle of your rotor period. When you start to spin fast, you can't necessarily do that. You can't make the pi pulse short enough. And all the pathology of pi pulses that Art talked about is relevant then. Okay. And so one pi pulse per rotor. And I'm asking you to tell me what that Hamiltonian looks like. It's a heteronuclear coupling. So we've been working with those, so you know what those look like. You have MAS, and you have a pi pulse every rotor period. What do you think the effective Hamiltonian is? You can try it to first order. That's just the average over the rotor cycle. You can try it to second order and see what happens. Okay. And we'll talk about it a week from yesterday. That make sense? A week from yesterday. You guys can let me or Anish know if you need an extension, if you start to work on it and you're not ready by Wednesday, but we'd like to do it with you next Wednesday. Okay. You assume there's no other terms. Don't get hung up on the CSA. Like, do what I did. Just pare it back to just this so that you can see the phenomenon. And there's a paper, and this is open. Everything is open book, right? If you want to read Andrew Bennett's paper and see how he did it, that's okay. Just rephrase the answer in your own terms. So these are a lot of different homonuclear sequences. But I feel like the field shifted. This is just one person's impression. From being this, 1,000 homonuclear sequences sprouting in different labs and nobody knowing which is better. And there are more. I mean, I just picked some here, and I'm not even saying these are the best ones, just ones that I'm comfortable describing without reviewing anything. And then there came this paper from Malcolm Levitt and co-workers where he talked about general principles. And that was kind of like a piece of daylight coming out in the whole problem. Like, oh, that's the right way to think about it. And he talks about classes of pulse sequences. And he talks about deliberately bringing in a term in the Hamiltonian and not letting the other terms through. Not like it was an accident. Not like it was like, oh, what just happened when I got to that spinning frequency? And it turned out that within these classes he defined, you can refine many of the pulse sequences we already have, which is sort of the moment you realize maybe this is the right way to think. He has a review article. It's in the Encyclopedia of NMR, which is a reference that if you haven't used it before, you should be using in volume 9. And the figures that I'm going to give you come out of that review article. I'm not changing them except to correct the typos that I noticed, okay? All right, so here's the way that paper lays things out. Start with table 3 at the bottom. When we think about the terms in our Hamiltonian that we either want to turn on or turn off, it is useful to talk about what spherical harmonic components are in there for space. He says for spin, yeah, or the RF, if you like. You can think about it either way. And then he says for field, which means B naught. Okay. So remember that out of a spin and B naught, we treated those as two L equals 1 objects that you could make an outer product of to have an L equals 2. Do you remember that? So that's what we're talking about here. Like go to the CSA, second one, okay? So the spatial was inherently L equals 2. That's just how it acts because it had 2 independent indices, the spatial term had. And then the spin was the outer product of the spin itself, which is manipulated by RF, and the field, which hopefully we don't manipulate. Everybody understands that when we come to we don't manipulate the field except to shim. Okay, so these two things together make a rank 2 tensor when you combine them. But he has disentangled them because he's trying to draw your attention to what you can control. So we're going to really zero in on this first, second, and third columns. And the field rank is just here for you to understand conceptually what's going on. We're now going to erase that and dig in on the first 3 columns. What can you control? What can you do to bring one of these out and push other ones back? And he's noticing that they have really different answer in terms of the space rank, that we should think about some having 2 and some having 0. Why is there 0 here? Well, that's an isotropic interaction. So there's just nothing that you can do spatially to it. There's one thing on this table that you could consider as an error or not, which is that all the J couplings have space rank 0. Why do you think I'm saying you might consider that an error or not? Can you say it again? It's a weak coupling limit. Yeah. But is it, what is the rank of that interaction? What do you think?
I thought it would be like the weak limit was 0 and like the strong limit was 2.
Yes. The strong coupling limit is probably 2. I don't know if there's a good reason it could be higher than 2, but I just don't think it'll ever be strong enough for that to matter. So what does it mean? That it has the truth is 2. What does that mean? Like as an experiment. If you can find something with a super strong J coupling, and I think in the material scientists in our department right now, we can actually find a compound to do this experiment if we want to. So something where the electrons are really special, but the nuclei are backed way the heck off each other. So they don't actually dipole. I mean, it's just so weak, okay? Or maybe, yeah, they're just very far away. In planar systems with conjugation, you can sometimes get 6 and 8 bond J couplings demonstrably, like Koji Nakanishi used to study. So, all right, so we'll get one of these material sciencey things where you've got like lots of bonds between them. So the dipole coupling is squat, but the electrons between them are really specially designed. Then you put out J comparable to D. It's an exotic case, but whatever. Now we have to think about what is J really? It's not in the weak limit, no excuses. Like what does it really act like? So if I took that system, it would probably be some Bucky something based, right? It'd be like one of those tubes that Colin Knuckles does or whatever. Now, if I put the tube in the magnet this way or this way, do you think J is going to be the same? Can't be. Perturbing electrons can't be. So J is a tensor, just like everything else is a tensor. I don't know how strong those anisotropies are, but I think the time has come that people could actually measure this. We don't care for proteins. We don't care about that. It's just not important enough. Even like with the weak residual dipole coupling, all those things, it's never big enough. It doesn't matter. So it's an approximation, just like you said, Chris. So J, we approximate it to be a number, a scalar, rotationally invariant. And what else is 0 in this table is the isotropic shift, and that's artificial because he's separated from the CSA as 2 different terms. So this one is, they're both coming out of the same physical interaction and have the same form as the Zeeman and as each other, but he's artificially pulled them apart. Anyway, now we have things that depend differently on space. They also depend differently on the spin. And so that is helpful to think about that. Now the table on the top, with a little bit, a couple things fixed, takes 4 terms that we might be interested in talking about for homonuclear recoupling sequences: isotropic shift, CSA, J coupling, and dipole-dipole coupling, by which he meant specifically and only homonuclear dipole-dipole. And each one has a space rank, and each one has a spin rank, and we are no longer keeping track of the field rank. So sometimes it'll look illogical, like you see that space rank of 2 is getting combined with spin rank of 1, and I told you never do that, right? But it's okay here because he left something out. It's like, of course it makes sense. So 0 is always getting matched to 0, not to 1. But it will look like we're doing something goofed up, like 0 is matched to 1 or 2 is matched to 1. That's not true because we just cut the last column. Now, each of the space rank or the spin rank has M values that we know about. So what he's doing is he's saying, could you take each one of the entries here? So in the first line for the isotropic shift, there are formally 3 different possibilities: 0, 0, 1, minus 1, 0, 0, 1, 1. So each one of these is an object with some rotational properties. And in describing that row, I have described everything, how it's going to react to every spin, every RF pulse you can imagine, every MAS. So I've specified completely how it's going to behave. And I should be able to tell you what pulse sequence elements would preserve it. And for the most part, different physical interactions have different combinations of these signatures. I think he called them spin quantum number signatures, something like that. So let's focus on these signatures and figure out a sequence that preserves particular signatures. Now, the weird thing here, and we've seen this already, even just in the little old selective CPMAS, is that we're going to be distinguishing different pieces of the same dipole coupling. That's one of the things we're going to do. Like, let's get this piece of the dipole coupling. I don't know what benefit, if any, that has. It's something for the field to think more carefully about. It just seems like a pain to me right now. But what I'm going to show you doesn't take on the idea, do we want the totality of this? And if so, how do you get that? Or do we want to distinguish each of those and what's that good for? It doesn't really attack that. What it attacks is, how could J behave differently than dipole-dipole? How could J behave differently than CSA? That's what it's going to do. So you see that there are marked differences. Let's take advantage of those and build a sequence.
And can you go back? Yeah. For the chemical shift anisotropy and dipole-dipole coupling, the space component doesn't have n equals 0 component. Is that true?
Why? Yeah. So here, there are 4 entries, and here there are 3 or 5. Yeah, why is that in this case? It's something I was making a joke about the other day. This is for the special case that you actually set the magic angle correctly.
Okay.
You were awake and alive that day. No, probably Eric said it for you, actually. Okay, so this is a longer table of the notes when you download it, or you should just go get his paper. This is a more useful one because I really like heteronuclear couplings, and they are included in here, I think, down at the bottom. Okay, and this first set, he was just talking about homonuclear, so now it's more complete. Once again, there isn't that field entry, so don't get confused as to why these spherical harmonics don't seem to match each other. They do. It just looks like they don't because he left that piece out because you can't manipulate it. Okay? Is that all right with everybody? Or are you just completely confused and I should go over it again? The pulse sequence. What insight did this give him? What did he do with the pulse sequence? This is very cute, and he's really good at these diagrams that illustrate. So what we're going to do is build up a pulse sequence element that gets repeated n times. So it's numbered 0 to n minus 1. It's repeated n times. Pulse sequence element could be simple. Like in the family of sequences, imagine that pulse sequence element is just 2 pi pulses. Okay, nothing else, just 2 pi pulses. All right, so but we're going to repeat that n times y. Well, it'll have a phase shift. The phase shift will be by some amount divided by n. Could be 360 divided by n. That would be simple. It could be simple. So n elements completes a cycle. So I've drawn, or he's drawn, a cartoon of a cycle. Now, here's the important bit. While you do that, the rotor's moving. The rotor will go through little n rotations, and little n and big N don't have to be the same number. So far we only looked for examples where they are something like integer multiples of each other, right? Like little n is double big N or the other way around. He's opening it up. He's saying, what if one is 5 and the other is 7 and they only meet every 30, whatever, you know? So he's opening up the window of possibility by saying, there's just two integers. Let's see how this works. And that turned out to be a better question than I think any of the rest of us intuited. So the Hamiltonian element will be preserved if, here's the selection rule, I'm not deriving it today. If you guys are really into this and you want to go over the derivation later, we can do that. It's hairier than the last problem we did, but M, N, mu, and nu. M is here. N is the number of rotor cycles. Mu is here. And nu was that phase change. Okay. M, N, mu, and nu. So mu and nu are two things that you control. I'm sorry. N and nu are two things that you control when you design the pole sequence. M and N. Give one more shot at it. M and mu, which are both kinds of M in two different alphabets. Those are spherical harmonic components. You say, I want that and that. I'm ordering up, out of a chocolate box. I want this spherical and that. So what can I do with my pole sequence? I can choose little n and I can choose nu. Another kind of n. I can choose those in my pole sequence. If I choose them so that this arithmetic works out, that z is any old integer, doesn't matter. There are rules about it, but let's just say for the moment, it's just any old integer. And that times capital N, which was a thing I chose for my pole sequence. So in this equation, nu, n, and capital N, those are under my control when I choose a pole sequence. M and mu are the spherical harmonic components that I wanted, and z is an integer, okay? When that equation is met, I get to keep that term. If it's not, it's going to 0. That is the fully generalized, I think. I don't think you can generalize any more than this. Maybe. For what we talked about in the specific example of Hartmann. This is kind of lensing out, like, what are all the different conditions that you could have? This tells you kind of the universe of it. It's beautiful to have that, especially for the homonuclear sequences. If you have a simple C element, like it just looks like 2 pi, one of the things that you have in specifying n, capital N and little n, is you have specified a relationship between the spinning frequency and your V1. You're going to hold a spin lock that has some relationship to your rotor frequency. We've already mentioned that you can't do anything you want with the probes here at NYSBC. You have to stay within the power limit. So this is a very practical constraint, and it is troublesome for the sequences that were first developed here. Now, the symmetry class that we're talking about here is called C sequences. So for these sequences, omega 1 is capital N over little n times omega r. So if capital N, which is again, how many blocks do we have for the RF, is a big number compared to little n, which is how many rotor cycles you've done in the same amount of time. Clearly, this is a problem. If you say, I want to accomplish a lot of RF when I didn't really spin very far, you're not going to be able to do this on a real sequence. It's beautiful on a computer. It doesn't work. Now, this matching condition has many, many solutions. I don't know if they realized when they first started working on this, how big the possibilities are. But this is really kind of cool to just sit back and say, oh, our FDR is one of those. Holy crap, there's all these things. Were we supposed to wait for Dan Raleigh to just like do all the knobs? Or like, what were we going to do otherwise if there wasn't like this order? So one of the things that was popular for a while is C7. So capital N is 7. Nu is 1 and little n is 2. So that means we have to really crank the RF up. So this was good for slow spinning. And some beautiful work was done, like applications, beautiful applications. This was useful. Now, this is designed, this read the small print here, this is designed to suppress CSA, isotropic, homonuclear J coupling, and to allow homonuclear double quantum recoupling. So when you pick the spherical harmonic components, you're kind of saying, is it double quantum or zero quantum, right? Remember that for the other problem? But it doesn't suppress everything. So one thing you can do, besides, I hope it's right here, besides put in a CN sequence, or I'm going to define another class of sequences in a minute, is you can use composite pulses. It doesn't have to be a pi or a 2 pi or a pi and a minus pi. The C element could be other things. And I think it was Niels Nielsen who came to him and said, you know, you should, like, you're an expert at composite, you should be using composite, by which I mean a small number of near contiguous RF pulses with different phases. It achieves a net rotation, which here we want it to be 2 pi, but it does it by an indirect pathway, you coming back and forth and whatever, but to get there at 2 pi, designed in such a way to compensate for something that you're worried about, compensate for offset, compensate for RF inhomogeneity, compensate for something that C7 didn't do anything about. So they used a so-called post element. This is an example of a compensated pulse sequence element, and instead of just a regular pi, and then they had this thing called post C7, and that was really great pulsing. You could also do something called supercycling. So if you have a repeated pulse sequence element, sometimes you want to phase flip it the next time around. So you do the same thing, but hit it with a net pi rotation. A good example for this would be if you were just going to do RFDR, that was just the pi pulses, the one you're going to have your homework on. Just hit it with pi pulses. Do you really want to have the same phase of the pi? Because if you think about it, this pi pulse is taking z to minus z. You could have any phase you want. That's flexible. There's a famous phase cycling of pi pulses for any sequence. It's better to do this, like 8 different phases, so-called XY8, and then you get rid of a lot of errors. So you can supercycle this as well, okay? So you can use a composite pulse instead of a simple pulse on the inside of it, and then you can supercycle the whole thing. Both of these, of course, do not confuse them with phase cycling. So these are things you do within each transient. Phase cycling would be now each experiment, flip the phase of the whole thing, that flips the receiver and you get rid of even different. So when you look at how complicated this is, remember that in addition, inside 0, you've got lots of choices. You could super cycle this within each transient. You can phase cycle it, experiment to experiment. We can get rid of anything we want, right? We can get rid of anything we want. I have to round up, like basically now. So there's another class of sequences, Rn, and it's different because you use a pi instead of a 2 pi, and that does a lot of good things for you. It doesn't remove as many artifacts, but what it does do is it takes power requirements way down. You can design something to preserve CSA and get rid of dipolar. So you can measure CSAs. This is something that Rob Tico did beautiful work on, and we did a little extension of his work here. So we're measuring CSAs site by site in ubiquitin. So these kind of homonuclear sequences can be used to do the working planes that are carbon-carbon, beautiful working planes. And if you put it together with heteronuclear, you have the basic 3D sequences that most solid state assignments are based on. I'm sorry for rushing. And nowadays we think about measuring proton and having that be the last dimension, the detected dimension. So you can walk through, and of course you always sensitize with the proton, but you can also end on a proton to detect. The last 4 slides came from some slides developed by Bernd Reif for the winter school. I just took his slides here for you to look at. And I'm reminding you of your homework and I have to run out the door.
Is proton really the last dimension without oxygen?
Oxygen's so much cooler, right? Okay, I have it.
Thank you.
Oh, thank you.